Welcome to Physics in Baseball. I'm Jake Seboly, and this is my PowerPoint presentation for Project 1. This presentation is going to be on the applications of physics in the game of baseball. All sports are governed by the laws and principles of physics, but the game of baseball is an especially good one to study because it has so many different events that happen, and they all can be described using the laws and principles of physics. In this presentation, I'm going to talk about 8 different events. As you can see, the pitcher delivering the pitch, the path of the pitch ball to home plate, the batter's swing, the contact between the bat and the baseball in the swing, the baseball's flight after it's struck by the bat, the effect of air resistance on the flight, the defensive player catching the ball, and the catcher catching the ball. Every play in the game of baseball begins with the pitcher throwing a pitch. He's standing on the pitcher's mound, and to throw the ball, he swings his arm, which increases the velocity of the ball, then releases it towards home plate. He also steps forward with his front foot, thrusting his leg forward to generate additional force. We can calculate the work done and the force done on the ball by the pitcher using the work energy theorem and Newton's second law. To find the work that the pitcher does on the ball when he pitches it, we can use the work energy theorem, which states that the kinetic energy of the ball after its pitch is going to be equal to the amount of work the pitcher does. So given the mass of 0.135 kilograms, which is a standard for professional baseball, and the pitch speed of 40 meters per second, you can see the formula, and we calculate that 108 joules of work are done by the pitcher. We can also calculate the force that he exerts if we know that his windup covered a distance of 1 meter until he released the ball. So he accelerated the ball from rest to 40 meters per second over that 1 meter, and using the kinematic equations and Newton's second law, we can get the force, which is 108 newtons. Now let's talk about the flight of the pitch after it's released as it heads towards home plate. A pitch of 40 meters per second takes approximately half a second to reach home plate. Gravitational force acts on the pitch as it travels and can cause it to drop a little bit. We can calculate that using projectile motion. Professional pitchers also throw a lot of different kinds of pitches, and to do so, they impart various spins on the ball. The spins generate a Magnus force, which causes the air resistance to be different on opposite sides of the ball, causing it to travel in a curved path. And they take advantage of that force to fool batters with curving pitches like curveballs, sliders, and breaking balls. If we assume, once again, the ball was pitched at 40 meters per second, and we assume a standard distance between the mound and home plate, 18.4 meters, then we can calculate 0.46 seconds is the time the pitch requires to reach home plate. Then we can use the kinematic equations to find how much gravity affects the path of the ball, and as you see here in this equation, we get 1.03 meters down as it travels towards home plate. Now let's talk about the batter. To swing the bat, the batter generates rotational motion in the bat by stepping forward with his foot, pivoting his body around that foot, and moving his hands and the bat likewise in a circular fashion. So the batter is exerting a centripetal force on the bat that can be calculated with the given formula. The tangential speed of a typical swing in professional baseball is 25 to 30 meters per second, but that depends on a lot of variables. Obviously, the strength of the batter. Also, the mass of the bat is very important. As you might think from Newton's second law, light bats are easier to swing at faster speeds than heavy bats. We can calculate the centripetal force that the batter requires to swing the bat. Let's say he swung it at a tangential speed of 27 meters per second, and he's using a average professional bat of length 0.9 meters, mass 0.85 kilograms. We can calculate the centripetal force to be 690 newtons, which is a very large force, and that's why strength is such an important issue for batters in the professional game. Now let's talk about what happens when the bat hits the ball. As you might expect, the bat exerts an enormous force on the ball at the time of contact. Often the ball rebounds off the bat at a faster speed than the speed at which it was originally pitched. The collision between the bat and ball is not easy to model as a partially inelastic collision because an outside force acts on the system. In this case, the batter's moving his hands and therefore still moving the bat. We can calculate the average force that the bat exerts on the ball using the impulse and time equation, though. It's interesting to note the speed of the ball after it rebounds off the bat is dependent on several variables. It increases if the speed of the pitch is increased, the speed of the bat swing is increased, or if the mass of the bat is increased. Let's calculate the force that the bat exerted on the ball. If we assume it was pitched towards home plate at a speed of 40 meters per second, and after it was hit, rebounded in the opposite direction at 50 meters per second, we can calculate the impulse to be 12 kilograms times meters per second, which doesn't sound that impressive, but when you find out that this change in momentum occurs while the bat is in contact with the ball, which is a time of only 1 millisecond, then using the force-impulse equation, you get a force of 12,000 newtons, which is definitely an impressive force. Now let's talk about the flight of the baseball after it's struck by the bat. This flight can be modeled using the principles and equations for projectile motion. The distance the ball travels depends on the y component of its motion, which is dependent on the angle of the horizontal at which it starts its trajectory. The x component of the motion is the batted ball speed, which is the speed at which it travels horizontally. As you might expect, a baseball travels farther if the batter hits it at a higher angle above the horizontal. This is because it'll stay in the air longer before gravity brings it back down to the ground. Also, as you would expect, it travels farther when its original speed is farther. You might expect a launch angle of 45 degrees above horizontal would be ideal for the farthest distance, but because of the effects of air resistance, that ideal angle becomes 35 degrees. Let's calculate the ball's displacement if it's hit in a strictly horizontal path with a batted ball speed of 50 meters per second and it's hit from a height of 1 meter above the ground. That means it's going to take 0.45 seconds, as we calculate here, for gravity to bring it to the ground, and in that time it's going to travel a horizontal distance of 23 meters. The standard Major League Baseball infield is larger than 23 meters. Thus, this ball is going to bounce within the infield and probably result in a ground ball out. Now let's see what happens if it's hit at 30 degrees above the horizontal. With the same batted ball speed of 50 meters per second, we can calculate the vertical component of its speed is 25 meters per second. This results in a time of 5.1 seconds before the force of gravity can bring it back down to the ground. During that time, it's going to travel 220 meters, which is easily enough for it to leave the ballpark for a home run. So you can see the big difference that increasing the launch angle makes on the displacement of the ball. The flight of a batted ball is impeded by friction from the force of air resistance, and this air resistance becomes a very important factor in the game of baseball. The actual displacement of a batted ball is less than what you would calculate through the kinematic equations because of this force, and balls hit at higher angles are more heavily impacted by air resistance because they're in the air longer. Because of this force, baseball games can be significantly impacted by the weather conditions that they're played in, because the amount of air resistance force varies significantly depending on factors such as the weather and the altitude of the game. Here's a look at some of the effects of air resistance on the ball and how different conditions affect that. A ball that would travel 400 feet in normal conditions travels 6 additional feet for every 1,000 foot increase in the elevation of the baseball stadium above sea level. 4 additional feet for every 10-degree increase in temperature because warm air is less dense than cold air. Travels 4 additional feet for a 1-inch decrease in barometric pressure. And if the wind is blowing in the direction of the ball, it travels 3 additional feet for every 1 mile per hour increase in wind. If the wind is blowing against the direction the ball is traveling, you lose 3 feet per mile per hour. Now let's talk about what the defensive players have to do. Once the ball is hit, a defensive player can put the batter out by catching the ball before it hits the ground. So, as the ball spends more time in the air, that's known as its hang time, the fielder has more time to get into position to catch the ball. Therefore, he can cover more ground and get to a ball that's farther away from him. That's why balls hit at higher angles are more likely to be caught than line drives. The average baseball fielder can run at a speed of about 9 meters per second. Thus, if the ball has a hang time of 5 seconds, the fielder can catch it if it falls within 45 meters of his original position. And finally, here's what happens if the batter misses the pitch and the catcher has to catch it in his mitt. To stop the ball, the catcher has to exert a large enough force to stop it, and we can calculate that using impulse and time. If the pitch is traveling at 40 meters per second and the catcher stops it over a period of 1/100th of a second, we can calculate that the catcher exerted 540 newtons of force. So, in order to decrease the force that the catcher has to exert by increasing the period of time that the ball stops, the catcher wears a special heavily padded mitt instead of a regular baseball glove, and that saves him some wear and tear on his hand as he is catching those hard pitch balls all game long. And here is my references page. Before we go, I just want to say the study of physics in baseball can be very fascinating. Some people, including some of the people that produce these references, have devoted their entire careers of research to discovering the full applications of physics within the game. However, even people with just a basic knowledge of physics can go out, play a game of baseball, and observe and feel the impacts of physics as they play.